So I pulled this problem from our textbook. The two loops in the figure have equal currents in opposite directions. What current will create a magnetic field strength of 350 microteslas at the center? All right, both of these loops are creating their own magnetic fields. The overall B at the center Sorry, my computer is lagging. This overall magnetic field at the center is going to be the vector sum of the magnetic field due to one of the loops plus the magnetic field due to the other. So let's go ahead and just say this smaller loop is loop 1. And the bigger loop is loop 2. Since we are finding the magnetic field exactly in the center, if we look at the test notes for the center, that's the B of a coil. I'm not sure why our author chooses to call one something different. I guess since they're accounting and saying we can account for more than one loop is probably why. So mu naught Ni over 2R. This magnetic field is a vector, but this equation in and of itself does not give me the direction. It just gives me the magnitude. Since both of these are single loops, the N in here is 1. A single loop, the magnetic field at its center will just be mu naught I over 2R. We will need to use the right-hand rule to determine the direction of the magnetic field. Because we're adding vectors together, we have to account for those directions. So B1. Maybe. I apologize. My computer is apparently very tired. So for coil 1, I've called the smaller coil or loop number 1. The strength of this field we can calculate. Mu naught is a constant. I remember the exact value. The 4 pi times 10 to the negative 7. You can use the rounded value in both the test notes or the textbook. That's totally fine. Now, we're not told what the current is, but we know that both coils or loops have the same current. So I'm just going to call these I. And then we'll be dividing by 2R. And we know R for this first loop is 1 centimeter. We do want it in meters. So we end up with some fraction times I. Now the direction of this field, we need to use the right-hand rule. Now there's 2 ways to do this. The right-hand rule, the original way that we have been taught, the right-hand rule, is to put the thumb of our right hand in the direction of the current. Now, when the current is looping like this, we have to just pick one location on the loop. So for example, if we think right here, this current is pointing kind of up and to the left a little bit. So put your thumb of your right hand, just have it line up with that arrow. When you do that, your fingers in here, in this region, are pointing towards you. So your fingertips represent the direction of this magnetic field. So when I align my thumb with this current arrow on this left side in here, my fingertips point towards me. This magnetic field is out of the screen towards me in that middle area. So that means at the center of that loop, this magnetic field points directly out. Now, because the current is doing the looping, there is another way we can do this. If the current is looping, we can let the fingers of our right hand follow that looping current. So I would look at my hand with my fingertips going counterclockwise, like this current is drawn, and my thumb represents the magnetic field in the center specifically, which is where we want it. So letting my fingers of my right hand specifically follow that current arrow. So I align my fingertips with that arrow. My thumb points out at me. It points out away from the screen. So either way is fine. Okay. This second magnetic field, due to the outside loop, we're going to use the same equation. It has the same current according to the problem. But it is twice as far away, so it has a different distance. The direction, right hand rule, whichever way you want to do it. We now want to look at this current arrow. Ignore the inner loop, ignore the other arrow. So this one doesn't matter anymore. Well, at the moment. If I use this second version of the right hand rule and let my fingertips follow this arrow, it has to be my right hand. It's a little weird to get my fingertips following that arrow because my hand doesn't naturally want to turn that way very well. But if I do get my fingertips following that arrow, my thumb points away from me into the screen. It points towards the screen. So this direction is into the screen. So these are in opposite directions, these magnetic fields. So if I'm adding a vector in the out of the screen direction, which could be the positive z direction, to a vector that points in the negative z direction, then we end up subtracting their magnitudes. So I'm going to assume, just to continue, a traditional coordinate system. In this coordinate system, z would come out of the screen. So B1 is going to be the positive z direction. B2 is going to be the negative z direction. What we want is for them to add up to give us a strength of 350 microteslas at the center. They're not telling us what direction. We can reason out the direction. This one, B1, is going to be bigger because it's closer to the point. So this magnetic field, we want these two fields to add up to be the 350 microteslas. I'm putting 10 to the negative 6 in for micro. So that's for this B at the center. That's going to equal B1 plus, but I have to account for the direction being opposite, the B2. So we end up subtracting it simply because it's in the opposite direction. Okay. Let's scroll up just a little bit here. I'm going to factor out the I, but I'm also going to go ahead and divide both of these by 2. So simplify the 4 pi part a little bit. There's no one right way to finish the algebra. So I'm factoring out, let me get rid of that, the I, because it's the same in both terms. So up here I have 2 times 10 to the negative 7. Nope, 2 pi. Over 0.01 minus. So I could technically factor out the 2 pi part as well if I wanted. Okay, so I'm going to end up getting current is just this 350 microteslas divided by what this number ends up being. I'm going to just go ahead and solve that out. Okay, I'm getting times 10 to the, that seems a little big. Let me plug it in again. So I'm getting, so to 2 sig figs, I'm getting 11. And then the units will be amps. We can show how those units work out. So as far as units are concerned, on the left side, we have teslas. So we're solving for this I, the units of I. The 4 pi times 10 to the negative 7 has units of teslas times meters over amps. That's the mu naught. And then we divide this by a distance, which is in meters. So when we well, we can first cancel and the t's. When we divide everything over, we end up with amps for our answer. So that's where those units come from. So the equation itself is not necessarily terribly difficult to use, but we do have to consider direction, and that requires that right-hand rule. So when we're finding overall magnetic field, we do have to account for the field direction in terms of adding everything up.